A very good day to you. Today we are moving on to electrodynamics, where we're looking at electrical machines. And these electrical machines can be, for example, generators and motors. I think you can see some diagrams that are right here on your screen that are representing some of those aspects. But come with me right on the experiment table. Let's take a look at this generation, just to demonstrate quickly what happens when electricity is being generated. As I am turning, you can see something is happening. The bulb is glowing. What else do you see? You see there is a magnet. You see there's something that's rotating inside or turning inside, which when I stop, if you zoom in, you can see that there are little coils inside and brushes as well as a ring right there. We'll talk about that in terms of its application in electrodynamics. All right, so that's electrodynamics, motors and generators. Quickly, as revision, in previous years, you've learned that magnetic field is associated with a current carrying wire. In other words, if current is coming out of the page, all right, we have got the magnetic field going round, and we call this the right-hand rule, okay? And if you have got current going into the page, you have got the magnetic field going round. These are the two examples that we talk about. If I have a wire in my hand, okay, and current is moving that way, it means that the magnetic field is going round like that. If I have current going inside the board, the magnetic field is going that way. Inside the board, we represent it by an X. There we go, inside the box, inside the board, and outside the board, the magnetic field is represented, the current is represented by a dot, and you can see the magnetic field going right round like that. So if we put a compass next to a current carrying wire, the compass is deflected. Why that happens is because the current carrying wire induces a magnetic field. It is from that end that we come up with motors and generators, all right? Where generators, basically, you must know, converts mechanical energy to electrical energy. And motors converts electrical energy to mechanical energy. So while generators are converting mechanical energy into electrical energy, your motors convert that electrical energy into mechanical energy. In other words, you can think of them as being the opposite of each. Here is a simple diagram that's just table that's just summarizing that. All right, there are two types of generators. There is what we call the DC generator and an AC generator. DC just means direct current moving in one direction. AC means that the current changes in direction. Motors are operating in the same manner. We got motors that use direct currents to convert electrical energy to chemical energy, and we also have alternating current motors that generally change electrical energy to mechanical energy. This must stick in our heads, and we must know it for examination. That part there actually comes from your exam guide. All right. May I make mention of also Faraday's law? In previous years, you must have learned Faraday's law, which explains that induced EMF is induced around a loop of conductor is proportional to the rate of change of magnetic flux through the area A of the loop. This can be stated as EMF is equal to minus number of turns multiplied by change of flux divided by change in time, which basically is the rate of change of magnetic flux. This is the law of electromagnetic induction, where we are producing EMF, or where EMF induced in a single loop is proportional to the rate of change of magnetic flux through area A of the loop. How do we change, how do we alter that EMF? We increase the EMF by increasing the speed of rotation. So if I am going to increase the speed of rotation, I'm going to increase the production of the EMF. As you can see, it's getting brighter as I'm increasing the speed. If I slow down, it just lights just but a little. Okay? What else? The strength of the magnet. If I increase the strength of the magnet, my EMF that I produce is going to be greater. Okay? If the number of turns are increased, it means that the EMF also will increase. Why does it increase? Because there will be more coils that are cutting into the magnetic field. These are three things that you must always remember, which are important for you to understand and answer questions. Like the question that I put up on the board. Let's start with the one right at the top, which says that, which one of the following actions will not cause an increase in induced EMF in a coil if the coil is rotated in a uniform magnetic field? So which one will not increase the induced EMF? Rotating the coil faster. If I rotate it faster, will it increase? Think about it. Look at it. If I increase it, what's going to happen? It increases the production of EMF. So A cannot be right. All right? Increasing the strength of the magnet. We spoke about increasing the strength of the magnet is increasing the value of the IMF. Increasing the number of turns, yes it does. Replacing the coil with a lower resistance. So in this situation, we are asking ourselves which one will not increase the induced EMF. All of these would increase the EMF, all right? So they will not apply as being the answer. Replacing the coil with a coil of lower resistance is the answer to this particular question. 1.9 here says, which one of the following changes may lead to an increase in EMF of an AC generator without changing its frequency? Decreasing the resistance of the coil. So we want one that leads to an increase in the EMF. Okay? Increasing the area of the coil. Increasing the resistance of the coil, increasing the speed of rotation. So there are three factors that we spoke about. If we decrease, the speed of rotation, it does not change the EMF. So what do you think will happen? If we are going to increase the area of the coil, it means that we are increasing the number of coils within the number of turns within the coil, and in this way we are increasing the value of the IMF. So the answer there is B. If we increase the area of the coil, we are going to have an increase within the EMF. All right, so that's a few questions to think about. Let's look at another set of questions right now. It says the direction of induced current in the coil of a generator depends on, the direction of induced current on a generator depends on length of coil. No, it doesn't depend on that. Speed of rotation of the coil. No, it doesn't depend on that. Direction of magnetic field. Yes, it is the direction of the magnetic field that it depends on. We start talking about the right hand rule. The right-hand rule gives us an idea of the direction. I'll expand on the right-hand rule just a little bit later on. Which one of the following energy conversions take place in a DC motor that is in operation? Okay, so DC motor, what does the motor do? It is turning electrical energy into mechanical energy. All right, so where is the answer? Turning electrical energy into mechanical energy. Our answer there is D. So that's a brief introduction to some questions that are to do with electric motors. All right, a simplified diagram of a DC generator. This is from the exemplar 2014, and a graph of its output potential difference for one cycle is shown. So basically, if you got a DC, one thing that you must know is direct current, okay, does not change in direction. In other words, while we are producing direct current, it gets to zero and it goes back again in the positive zero, and then if there was another turn, it would have gone in the positive and come down to zero and back up again. It doesn't come down in the negative. The one that comes down in the negative will obviously be for the AC current. Okay, so it's only the AC current that will go down into the negative. So below we've got a DC current, and this DC current is the one that is in action here, all right, being generated. The question says write down one way in which the output of the generator can be increased. We already have three ways that we can increase the output. One of the ways is increasing the speed. The other way is increasing the strength of the magnet. The other one is to increase the number of turns within the coil. That in itself increases the potential difference. Okay. Now, as I mentioned earlier on, we said that if it is an AC generator will have production of potential difference also in the negative. All right? So this will be an AC generator. Okay. By now, we must be able to explain what is the difference between an AC and a DC generator. Okay, an AC generator will show slip rings, all right, while a DC generator has got split commutator rings. Think about that, that's very important, all right? Let's go back to the other slide with the question and try to make sense of it. It then says, does the generator have split rings or slip rings? Think of it, the graph is coming from positive and then to negative. Which one has got slip rings? It is the AC generator. Which one of the following diagrams below, A or B, shows the position of the coil at time 10 seconds? All right? Now, what happens with Faraday's law is that we have got the production of EMF as the coil is moving within the magnetic flux. All right? The explanation is when it's vertical, all right, very little of there is actually no production of EMF. So while it's turning from vertical, it is increasing in EMF production, and at its horizontal, it's got the highest production of EMF. All right? So when it turns back again to vertical, it then has a EMF of 0. So here is the direction of the magnetic field. All right? Which one of the diagrams below, A, B, OB shows the position of the generator's coil at time t equal to 0,1 seconds, which is right here. Potential difference is 0. When it's in the horizontal, when it's in the same direction or parallel to the magnetic flux, we have got the highest amount of, in other words, we've got what we call V max. All right? This is V max. So because it's alternating, it will have different V maxes at the bottom and at the top. What negative is just telling you about is it's just telling you about the direction there. All right. Now, where will we have the position that's demonstrating 0 volts as the potential difference? Obviously, it's going to be diagram B when it is at 90 degrees. I hope you understand that. I'll continue to repeat that and explain that as we go on because it's very vital in our understanding. A DC current passes through a rectangular wire, loop OPQR, placed between two poles, as shown in the diagram. Which two segments of the loop will experience an electromagnetic force when the loop is in the position as it is? Okay, so obviously in that position, the loops that will experience electromagnetic force are right here, P and O, Q and R. Let's see in our answers if we got that. So they got it as OP and QR. Exactly. These are the parts where it will experience magnetic what? Magnetic electromagnetic force in these two loops. Our answer there is C, OP and QR. All right, next question or illustration that we have is of the right-hand rule. The thumb shows the direction of the magnetic field. Okay, it's already written magnetic field, while your forefinger shows the direction of the current. All right, and the B there is showing the direction of the thrusts. Okay, so consider that diagram and think about it because we're going to use it in determining the direction of currents, the direction of magnetic field, and the direction of the thrust of a motor or a generator. Look at this galvanometer that is joined to a coil, and there is a magnet that's being moved in and out. Okay? What is going to happen? Obviously, the galvanometer is going to change direction left and right as you move in the magnet up and down, up and down, up and down, right? Inside the coil. Okay? In other words, we are producing EMF there. A teacher demonstrates how current can be obtained using a bar magnet, a coil, and a galvanometer. The teacher moves the bar magnet up and down. Briefly describe how the magnet must be moved in order to obtain large deflection of the galvanometer. All right, so how does he move it? We still have the same type of magnet. We still have the same number of coils. What other parameter can we change of the three parameters that we spoke about that can change the EMF? That will be the speed in which the teacher moves that magnet, okay? So the speed of moving the magnet. All right. Write down the name of part X on device A. Now, device A and B below operate on simple basic principle. What is the basic principle that these two operate on? Okay, electromagnetic induction. Yes, well done. All right, and you can see these are what we call, for X, they are what we call the split commutator or split ring commutators. Some books just have them as split rings. Okay, you can see they are split rings, or other books have them as commutator rings. All right, so that's one example there of a question that you can come across. All right, so as I had said earlier on, generators change direction. As current changes direction, the slip rings remain connected to the half of the coil. That is the slip rings here. For an AC generator, current goes back and forth in every turn. That's why we come up with a graph that looks like that, okay? And then for a DC generator, we've got the brushes. They are connected to the split ring commutators, and that's why you would come up with a graph that looks like that, okay? And so forth and so on. All right. So this ensures that the coil turns in the same direction, okay? In fact, this ensures that we got current. If it's a generator, this ensures that current moves in the same direction. That's a generator. This part will be for your motor. We'll talk about the motor a little bit later on. All right, so that indicates what's happening within this situation. We can actually tell what will be the direction of the current, what will be the direction of the magnetic field, all right? And we'll look at those examples. Magnetic field, all right? If we look at this example, all right, as it turns on the horizontal, to the horizontal, we've got its highest. Back to the vertical, it becomes 0. Turns back again to the horizontal, it's increasing, and back to the vertical, it's decreasing. We can have a graph that's relating A, B, C, and D again. All right, what's going on here? All right, which one of the following arrows shows the direction of the force experienced by the conductor to the magnetic field? All right, so we got a conductor here, we got the magnetic field there. We know that, right, which of the following arrows will show the direction of the force, okay? If that's the direction of the magnetic field, in this instance, we are going to use our right-hand rule, okay? What does that tell me? It tells me that the magnetic field is going to be moving in this direction, okay? And the conductor is showing current going inwards, all right? Okay, the current is moving inwards. Okay, so my B is the correct answer, showing the direction of the force of the conductor. The conductor is going to move upwards. The answer is B. You can refer to the diagram that shows the right-hand rule for you to clearly understand what is going on in this diagram. The graphs that indicate AC generator, Okay, I've spoken about them, how they change, they alternate in direction, and a DC generator, as well as the magnetic field, all right, and the position of the coils are given corresponding: A, 0, B at the highest, C, again 0 when it's vertical, all right, and then when it's turning towards D, all right, it starts increasing at the highest from D to A when it becomes vertical again. We can also turn the graph around and represent it like that. It's still the same thing because we still have Vmax, but it has to be just on one direction, on one side. It is not alternating. Okay. Motors, on the other hand, I need an example of a motor. Motor, as current changes in direction, we've got an AC motor, all right? The slip rings remain connected to the half part of the coil. Current goes back and forth, all right, at every turn, okay? So what happens to the motor is that it goes back also and forth, all right, like our starter's motor. DC motor, coil turns and the brushes touch each of the half rings, and this ensures that the coil will turn in the one direction. These diagrams we must be familiar with. We must already know what defines or determines a DC or an AC motor and what determines a generator and a motor. Uses DC generator, like the alternator in cars, an AC generator, electric generation from power stations, hydropower stations, and a DC motor, like the battery powered fan, all right, it's in one direction, all right, and AC motor, like your starter motor for a car, it changes in direction. In your exam, you're required to be able to give an example of any of these questions. All right, now in our next lesson, we need to have an idea of what happens when we start looking at RSM, all right? And I will give you formulas that are to do with those particular calculations so that you know what's going on in those situations. A generator is shown below. Assume that the coil is at a vertical position. So we got a generator, and the question says, assume that the coil is at a vertical position. We are now attempting questions that are to do with a generator found in our exam. First of all, let's think about it. What type of generator is this? Okay, it's got split rings. Therefore, it is the generator an AC generator or a DC generator? Give a reason for your answer. Okay. It is a DC generator. Why? Because it has split rings. Or commutator rings. Okay. 9.12 says sketch an induced EMF versus time for one complete rotation of the coil. The coil starts turning from the vertical position. Now our graphs, we must know that if it is a DC generator, you have your EMF on the y-axis and your time on the x-axis. What is going to happen basically is that you are going to have, if this is half a turn, the generation will be on one side So I will draw my graph like that. Okay, that's a singleton. We have looked at such an example of a graph. It can be a graph, just to be make it look nicer than mine that's drawn up there. It will be a graph like that or a graph like this, all right, which is showing you what is happening as the generation is taking place. All right, now that question is done. Let's move on to the next part. It says, write down the energy conversion that takes place during the operation of this DC generator. Okay? The operation of the DC generator. What is the energy conversion that takes place? I just need to read the top part so that we can have clarity on what's happening in the question. Okay, so the question says, the diagram below shows different positions A, B, C, D, and A of the coil in a DC generator for a complete revolution. The coil is rotated clockwise at a constant speed in a uniform magnetic field. The direction of the magnetic field is shown in the diagram below. All right? Write down the energy conversion. So what happens in a DC generator? We convert mechanical energy to electrical energy. You can write that in full. Now sketch a graph to show the positions, how the induced EMF of the generator varies with time, clearly indicating position A, B, and C. I can use the same graph here, just so that we can save time, 10.12, and say my part A is here. At the highest, I've got part B, and here I've got part C, part D, and A again. I can also invert that graph, and that will be my A right here, and B, and C, and D, and A. So that's the graph that's showing the generation, either of them showing the generation of the EMF over time. All right, that's just a sketch. Doesn't need to be accurate, and you'd get your full marks for that particular question. Okay, now that's a brief introduction on our DC and AC generators. By now you must know the differences between an AC and a DC generator. In the next lesson, as I promised you, we are going to cover aspects of calculating the root mean square, as well as P average and other questions that are required for you to know in an exam situation. This is your man Chibs, and from me and the team,